Hi everyone, this is the presentation for the system I submitted for the SIGTYP 2022 share task. I'm gonna briefly report on it following the paper I wrote for the proceedings, which I refer you to for more details. The share task aims to predict cognate reflexes from 10 language families. Cognate reflexes can be defined as word forms assumed to derive from a common ancestor word form, which can be attested or reconstructed. To give you a clearer idea, the table shows a few entries for the languages belonging to the Berta family. Each row contains cognate reflexes written in the APA, and what participants are asked to do is to find the missing cognate reflexes that are here signaled by the question marks. The dataset comprises 10 language families. Each language family is represented by 5 term files because each of them contains a different percentage of missing data, from 10% to 50%. This repartition is meant to test the robusticity of the models. Clearly, the more the missing data, the harder the task. Each of the 5 term files is matched by a test file with entries similar to the ones I showed you earlier. The 5 term files have overlapping data, so they have to be kept separate when training the models. Data is highly sparse because a row in the original data can contain more than one empty cell. And crucially, as the previous table showed, one major difficulty is that there is no single target language for each language family, but values of all languages need to be predicted in turn. A high number of models requires to be built for each language family because, as I said, the term files need to be kept separate and the target variables correspond to all languages of a language family. Therefore, the exact number of models for a language family is given by the formula number of languages multiplied by 5, that is the number of the term files. In order to tackle the issue of sparsity, I propose to remodel the original tabular structure into a new one where each data point corresponds to a single predictor cognate reflex plus its language label. This means that one single row in the original data is fragmented into more rows depending on the number of predictor languages for a specific target language. The table shown is an example of a new table where the original data rows are rearranged as to get one single predictor language and one single target language per row. This restructuring implies that one single row in the original data corresponds to more rows in my new tables, and therefore each of the new rows singularly predicts a target value. At inference time, as I will show, the final target value is computed by averaging over all of the target values predicted for a given row in the original data. I propose to use a transformer. As the image shows, it consists of 2 components, an encoder and a decoder. The input for the encoder are the cognate reflexes used as predictors after being vectorized as character embedings. Their positional embedings are also computed in order to incorporate the positional information of each character into the model. Indeed, the transformer architecture does not process the characters through recurrent layers, so positional embeddings are a way to encode positional information into the model. The heart of the encoder consists in a multi-head attention layer enabling to create a context-aware representation for each character. The output of the encoder is then merged with that of the decoder via another multi-head attention layer. More precisely, the encoder tensor is used as the key and the value of this multi-head attention layer. On the other hand, the decoder is meant to first process the target string via, let's say, a smart mechanism whereby the target characters preceding a given target character are used to predict this given target character. This is made possible because the target embeddings are passed to a masked multi-head attention layer, which prevents prediction from the future. Finally, before the output of the decoder is passed to the final densely connected layer with a softmax activation function, it is concatenated with the one-hot encoding for the language label of the predictor cognate reflex. As I anticipated earlier, at inference time, the outputs of the cognate reflexes of one row in the original data are averaged. The tables show the results for the data with 10% of missing data. All the results can be found in the paper. So here we can see the edit distance, the B-cube F scores, and the blue scores calculated for each language family. The scores for the transformer are similar to the baseline ones written within parentheses in the first table. The performance of the transformer is not among the best ones if we compare it with that of the other systems, as the second table shows. These tables show that the performance even worsens with higher percentage of missing data. We can conclude that all models seem to suffer from high variance, even if to a different degree. This is also due to the fact that the test data were released with the trained data, and therefore models have been built using test data as validation data. The transformer offers a theoretically strong way to model the data. We modeled the position of each character and created a context-aware vectors, but overall it seems to overfit. More experiments with hyperparameter tuning may lead to better results, but simpler architectures also seem to perform as well or even better. It has to be noted that at inference time, the transformer turns out to be computationally expensive because prediction of a character sequence requires a huge amount of dictionary lookups, which can only be run on CPUs. Thank you for your attention.